So today we will talk with the step-up converters. They are also called boost converters, and as the name suggests, they are used to increase the output voltage, with respect to input voltage. So technically, it is possible if you have a 5 volts input, you can get 12 volts or 24 volts output voltage. So you can get a higher DC voltage than your input voltage. So actually this is seems like inconvenient, so let me directly give you the circuit. So the circuit is like that. So the number of components and their types are identical to buck converter. So we have one inductor, one capacitor, one diode, and one MOSFET or a switch in general. So again, that MOSFET and that diode works in pairs, so they don't conduct at the same time. And the only difference, as you can see, is like the order of those things are changed with respect to buck converter. So now our inductor is directly connected to the input side, and we have diode like in that orientation. So previously it was blocking the input current, and again, in order to filter out the output voltage, we have some capacitor and we can have a resistive load. So now let's talk about how it works in general, and I will show you the operating modes. So again, let's assume we close that circuit. Once we close that circuit, the interesting thing is we have the inductor, and the inductor is directly short-circuited through input. So you are charging the inductor, and inductor current is increasing and increasing. Okay, so that's one important thing about boost converters. If you just keep them at on position, the MOSFET at on position for a long time, they will keep charging up, and at last you will destroy your MOSFET or your inductor or your voltage source. So at some instant you need to turn off your switch. So then you are closing that switch, but now our inductor has some finite current, and now that current cannot flow here because it is open, but it has to go to somewhere, because otherwise we will have large induced voltages. And actually we have that diode path here, so now that current will flow through here, and of course it's the same mechanism. So for that amount of time you can supply the load and also charge up the capacitor as well, and then during that one you are discharging your inductor, and it is going down, and then after some time you are again turning on that MOSFET. Now again you are charging up that inductor, but at that instant now that current they are like separated, so you are charging the inductor, and at that instant your capacitor is supplying your load. So basically these are the main two operation modes. So let's have a look at in detail of those on and off states. So again, then on state, this is identical to what I did. So in the on state we have the MOSFET, so S is on, and we have the diode here, and diode will be off. We will discuss why this has to be off. That's for now. Let's move on. And in the other state you have the switch here, so S is off, and you have the diode here, so diode is on. Okay, so we have basically two states. One of them you are charging the inductor and the capacitor is supplying the load, and once you charge the inductor, then all that inductor current is going to charge the capacitor and also the load. Okay, and actually before moving on to mathematical calculations, I would like to show you like really similar analogy using water and hydraulics. So there's a mechanical system working in the same way. They are called ramp pumps. Okay, and ramp pumps, again, it's it seems like unlogical, but you can pump some water at that level, and you can pump that water to a higher distance, so you can get a higher input voltage, without using any external amount of energy. I mean, it seems like, how can you pump some water to a higher degree? So let me show you the videos. So this is how ram pump works. So it is really similar to our boost converter. So we have basically a high, here I think you can see the water coming in. So the long pipe behaves like a inductor, and on, I don't know where side, here you see a single wave valve. So that valve is opening and closing, so that thing is like our diode, and above that this is another switch, and that switch again opening on and off. So these two things are working in pairs, so there are diodes and MOSFETs in our case. And on top of that you have a water tank or air tank. As the water levels goes up, so you create a pressure over there, so that is like our output capacitor in that manner. So let's have a look at how it works.
Water is driven into the pump using simple gravity and closes the waste valve, creating a high pressure.
You are creating enough pressure. Now you charge your inductor, and then there is no way that it can go, so it just climbs up. So it just turns on
through the pump
body,
body, opens
switch.
the delivery valve,
So then
enters the pressure chamber,
charging up the capacitor or increasing the pressure in that tank.
The air in the column.
And once it has some high pressure, and then the speed of the water now has reduced, so that valve will close due to
closing
voltage here. So that is like the diode. Sorry, I think at first I gave it wrong. So now that diode closes up, then your water keeps accelerating, and then
goes up through the delivery pipe. Then the pressure falls in the lower part of the pump, and the waste valve opens, allowing the water again to flow down the drive pipe. The wasting valve closes once more. The
see a
delivery valve
practical
opens,
thing.
and
It's
the
the
cycle
same
starts again.
logic as a boost converter. So that guy is doing that one. Let's see it in action. So it uses some kind of bottles as the pressurized tank, as a capacitor, if you see, and these are like you have one-way valves, and then this is your low level tank, and then you are getting water, and then you have this valve, and this is you have just two single side valves in that one, and then we want to pump the water up there. And again, if you think you cannot have 20 liters of water, and you cannot pump it like 20 liters of that water up to 5 meters high. So the trick is you are dissipating some of the water, so you are getting the potential energy from that water, and you are only using a small amount of water to pump into a higher distance, because again the water, the volume of water cannot be changed, but it's not identical to electrical system. Anyway, let's see it in action. So you open it, and then it just start tickling. It's like your switching frequency, right? On and off, and then you are turning on your output supply. Again, you are maybe dissipating most of your water, but at the end of the day, you are, the length of the cable is like the inductor, because once you have accelerated that water, it is like in the early weeks I gave an example of like having that train. So once you accelerated that train, you cannot stop it instantly. So it is the same with the waters, and actually you can feel it at your homes. I mean, if you just turn on the pipe and close it immediately, you know, the pumps can shake, and especially if they are flexible and that kind of things. Anyway, so now it is dissipating and you are having some pressurized air in the bottle. And yes, you are having some, you know, even it is tiny, you are using that water, you know, pumping at a higher height, higher altitude than the initial one. So it is, you know, gaining potential energy, but of course, you know, you are dissipating most of it. Again, there are like a couple of practical applications. So let's see a real world application. So this is an agricultural pump. So if you have, you know, large amounts of water in a river or that kind of things, so you can use that water. Again, you are dissipating most of it, but at the same time, you know, you can deliver, you can pump. This is where you ram pump it, and you are pumping to a higher position, right? And the sound that you are seeing is again the switching frequency of your ram pump. Okay, cool. So, you know, it is the same idea, and they are, you know, using the inertia of the water like we use the current in the inductor. Anyway, so let's move on to analysis of those things. So again, we will use the same trick. So if it is working at the steady state conditions, then I can get the inductor voltage, and I can integrate it over time. And if it is working at steady state, that should be equal to 0, because, you know, it is the voltage seconds balance of an inductor. So we will use the inductor voltage to get the output characteristics of our converter. So then how can I write the inductance voltage? So at first, let's have a look at here. So what is our VL? So VL is directly connected to our input side, so that is equal to VD, right? So in this case, it is equal to VD. And what about here? So we have here V out and we have VL. So VD. So VL is equal to VD minus VO. I mean, just by looking at that equation, I mean, you should be able to say that, you know, VO should be higher than VD. Why? Because if it were otherwise, if VO is smaller, then here our inductor will be seeing like some positive voltage. I mean, that's positive voltage as well. As long as you have some positive voltage, IL should keep going up and up. But that is, you know, not a steady state operation. You know, what is the steady state operation? IL can go up, then it will go down. So I mean, this is where it is charging, and so it needs to be discharged in the next cycle. In order to get discharge, VL should be negative. In order to have a negative voltage, that implies VO is larger than VD. But how much larger? So let's try to find that one. Okay, so let's try to find that one. And by the way, if you want to try it yourself, you know, there's a link to online simulation on Plexim, so you can play with numbers and duty cycles to get the output voltage characteristics. Anyway, so let's have a look at that one. So again, when it is at switch is on, diode is off at that point, and here switch is off and diode is on. Okay, so when switch is on, this is our inductor voltage. Okay, then that is our VD, okay, because it is what I see on the inductor current. And how long does it? This is for T on. or it is for dTs. Okay, and then again in the discharging side I see VL is equal to VD minus VO, because here is VD, this is VO, and that needs to be negative in order to have that area A should cancel out the area B, and that one is, you know, VD minus VO. So again the analysis is simple. In order to have steady state, so it will, you know, you have a constant DC, this is our inductor current, so it will be charging up linearly because you are applying a constant positive voltage, and then when it is going down you are discharging linearly. Again, in that assumption, you know, capacitor is quite large, so output voltage is not changing. So in a real transient, actually there will be some ripple at the output voltage, so it will be more or less like second order differential equations, but assuming that ripple is small and I can get a constant voltage with linearly, you know, discharges our inductor. Anyway, so again area A should be equal to 0. I mean, one trick here is if you are just going to use real area terms, okay, you need to get this one as like VO minus VD, or if you are going to use the real terms, okay, then you need to say A plus B is equal to 0. I mean, not in terms of real areas, but I'm just writing the mathematical equation. So let's write that one. So we have VD times dTs, okay, plus VD minus VO, and again this is for T off time, so that one is 1 minus D time Ts, and I can write 1 minus D Ts is equal to 0, and Ts will cancel each other. So let's write that one, VD times D, plus I will write VD minus VD times D, okay, then minus VO, okay, then plus VO times D is equal to 0, and that one will cancel each other. VD plus, or let me write like that one, sorry, let's move the VO to other side, VO 1 minus D, okay, and I can write VO is equal VD divided 1 minus D. Okay, let me get rid of myself. So here, as you can see, I have the output voltage as a function of my input voltage and my duty cycle. I mean, here again you can see again D is less than 1 and 0, and if you put it here you will have VO is larger than VD as our initial prediction. So again, if you just put D as 0.5, so VD divided by 0.5, you will have twice of the voltage of your input voltage with duty cycle of 0.1. okay, if you apply a duty cycle of 0.9, okay, this will be 1 minus 0.9, and so it will be 1 minus 0.9, so you will have 10 times of your duty cycle. But you need to be careful when applying a 0.9 duty cycle, because for 0.9 of your all period you will be charging your capacitor, and then you will be charging your inductor, and the inductor current can be high, so the current rating of your MOSFET should be capable of doing that. And again, you can say, okay, if I apply a 0.99999 whatever duty cycle, yes, technically you will have infinite amount of voltages, you will have a really high multiplication, but we will see it is not the case, because of non-idealities in the system. You will have some resistive components in the inductor, there are some losses in this converter, and also your capacitor has some non-idealities. But anyway, if you are working like around 0.5 or something like that, then you know that voltage relation is more or less accurate. Okay, so let's move on. So I mean, this is the same equations like I did, and you have that equation, and again from the conservation of energy you can say, you know, you can have the similar ratio like inversely proportional with some current. So yes, you are increasing the volt. I mean, in the buck converter, remember, we are reducing the voltage, but the output current will be higher than input current, you know, the assuming like 100% efficient converter. And this is inverse of the buck converter in that way. Yes, our output voltage will be larger than our input voltage, but we will be delivering the same power, so we are not increasing any power. So you are drawing more current, from your source. Actually with the practical ramp pumps it was the same. You are drawing more water, you know, with the low level, and you will be able to pump a less amount of water to higher distance, so we will be able to send less amount of current to a higher potential. So it's the same relation in that manner. Okay, so now let's talk about the condition to pass to discontinuous conduction mode. Again, you know, as long as you are aware of that transition, or if your controller is capable of keeping the voltage constant during discontinuous conduction mode, it's not a bad thing. But you need to be careful about discontinuous conduction mode, as we will see our voltage relations is changing. Okay, so let's look at the instant. Where we have just between the continuous conduction mode and discontinuous conduction mode, and that is the instant where your inductor current is just touching zero at that instant. Okay, so let's try to find that instant. Okay, so here I assume our, you know, boundary between the continuous conduction mode and discontinuous conduction mode is here. So I will try to find that value. Okay, and again from the graph you can see that if it is starting from 0, then you have the IL peak, and that value ILB is equal to half of that IL peak. Okay, I mean, it's just, you know, you can use the triangular rules, and that is half of it. So the idea is, how can I find that value? Actually it is starting from 0, and I know that voltage VL. Okay, here VL, remember during on time it was equal to input voltage, VL equal to VT, and if the current is keep increasing during that time, I can find the peak value. So IL peak, okay, is equal to VD, okay, and divided by L times T on, or you can write VD divided by L times D time TS. Okay, and again, if you don't want to write that thing in terms of our input voltage but output voltage, you can, if you just go to previous slide, I can write VO in terms of VD, right? So VO is equal to VD divided by 1 minus D. So I can use that relation and put it here. So IL peak, okay, is equal to VO times 1 minus D times D times TS divided by L. Okay, and actually I can use the boundary current here. So ILB, boundary between the continuous conduction mode and discontinuous conduction mode, is equal to VO times 1 minus D times TS divided by 2L. Okay, so again, just to discuss the transition, so as the output voltage, okay, as the output voltage, oops, sorry, I think I forgot the D here. Okay, so having a higher inductor will let you to run at the continuous conduction mode at slower currents, or again, if you have a smaller TS, then you will have a, so again, in this case, if you have a, again, changing your switching frequency will have a different effect, and that thing, again, you have a not as simple as relation with your duty cycle as in the buck converter, and it is 1 minus D times D. And actually, if you would like to write not in terms of the output voltage, but in terms of the output current, remember there's a relation between that one. So I can write the I output, this is your inductor current average, so this is your input current. That is one thing in the boost converter. Let me open the schematic again. So in the boost converter, your inductor current is directly equal to your input current. Whenever inductor is getting some current, it is drawn from source. So let's get rid of that thing, okay, and let's write that thing in terms of the output boundary current. So this is the output current, okay, and I can use that relation. So this is input current, which is equal to inductance current, so this is output current. I can put that relation to here, and I can write that one is equal to TS times VO D times 1 minus D, and there's another 1 minus D coming from the current relation, so it is squared divided by 2L. Okay, again, you don't have to memorize that thing, but let's have a look at what kind of graphic it will result. Okay, so here again, if you just look at the input boundary, so you will have that kind of graph, but again, this is your duty cycle, and this is how your boundary at the output changes with duty cycle. And for output current, there's a maximum of value around 0.3. okay, so again, getting lower than that value or higher that value will get you into continuous conduction mode. But if you are operating here, and if the current gets smaller, then you will get into discontinuous conduction mode. Anyway, so this is just to show you, and let's look at how does it work. Again, I'm not getting into analysis, but just to show you the current characteristics. So now we passed that boundary, and we are getting into discontinuous conduction mode. So again, our current starts from 0, and it just reaches some value. Okay, so this is normal our DTS. So in this point, our S is on. Okay, then normally this is our 1 minus the TS, but since our average current is lower, remember this continuous conduction mode occurs at light loads or when the resistance is high, and if the average current is low, so you will have less time to discharge, and if that time is shorter than 1 minus the TS, again due to diode, okay, we have a diode, it cannot go into negative region like that. Instead, it will just stay off like that. So during that mode, let me go to the initial slides. Okay, go that one. So during that time, so inductor current is off, switch is off, that is off. So you are again completely disconnected from your source side, and during that instance, capacitor is supplying the load. So if you want to achieve a low ripple voltage for this continuous conduction mode, you need to be careful about your capacitor size. Okay, so again, during that time, let me write here. So only C supplies the load. Again, actually depending on the load, there are some instances where you are giving less and less current from the inductor, and capacitor is already supplying, but still at that range, inductor is doing its bit to give some current, but after it is completely off, then you just left with your capacitor to supply the load. Again, I advise you to run those simulations with it was available in the presentation, and you can play with different parameters with duty cycle, and you will see how it behaves in the discontinuous conduction mode. Again, let's have a look at here. I mean, this is how it moves. Okay, if you are going to have a constant, in order to have a constant output voltage, let's say here you are applying a 0.75 duty cycle, or let's go with that one first. So you are applying a 0.5 duty cycle. So in this line, so V output is equal to 2 times VD, right? Twice of your input voltage. And if again, apart from that line, you are in the continuous conduction mode, so your voltage doesn't change. Okay, so your voltage doesn't change, and the relation that I just showed you, so in the discontinuous conduction mode, okay, so your output voltage is equal to VD divided by 1 minus D. Okay, but if you are just getting into discontinuous conduction mode, and if you just keep the duty cycle same, you will start getting a larger and larger voltage. So if you want to still keep the output voltage constant at twice of your input voltage, you need to adjust your duty cycle. Okay, and again, this is you don't have to know the exact characteristics of that thing, because again, that characteristic is changing with respect to duty cycle or the load parameters, but that shows a clear requirement of having again feedback loop. You need to measure the output voltage, and if it is higher than what you expect, then you can, here you start with 0.5 duty cycle, but now here, for example, if you want to operate at that current, then your duty cycles needs to be reduced to 0.25. If you just keep at 0.5, you will get a higher voltage. Okay, and again, if you just plot the let me show, I said V out is equal to, we said, VD divided by 1 minus D. Okay, if you plot that graph, it will give you, let me say, this is V out and this is duty cycle. So when duty cycle is at 1, okay, when it's at 1, so it will reach to infinity. Or when duty cycle is 0, okay, when it is duty cycle is 0, you have the VD voltage here, and it is going like that. Okay, again, this is the ideal case, but again, it is not really possible to have infinite voltage using that one. So this is what you expect from your ideal 1 divided by 1 minus D curve. But after some time, okay, after some time, let me draw here. Yes, you have your inductor and you have your diode here. Okay, but this is not an ideal L, so you have some resistive components. Okay, let's say this one is parasitic R of inductance, so ECR of inductance, and again you can have some R here, you know, parasitic resistance of R, and again you can have some voltage drops here, voltage drops there, but due to all those parasitic elements, if you really look into a practical boost converter, yes, it will follow that curve nicely along some time, but afterwards it will, you know, keep diverging from it, and even if you just increase and increase, you will have zero voltage. I mean, that is you know, what you expect actually, because if you just keep it at on, okay, if you just make it at 1, due to cycle 1 means you are just, you know, keeping that voltage, so you are just having VD voltage, and it's a short circuiting your inductance, and this current in the MOSFET will go to infinity, or if there is some resistance, it will be like DC VD divided by very small series resistance will be the maximum current. But anyway, if you just keep it here, then your load will be completely separated from your source, so there is no way of sending power at due to cycle 1. So again, in realistic case, why, you know, you will discharge your capacitor and you will see zero voltage. Okay, and again, it doesn't really make sense to increase that voltage to 1000 times. You will have losses, but again, you know, boost converter can be easily used to increase your input voltage to 3 times, 4 times, or maybe, you know, 5 times, so within reasonable values. Okay.